Okay, good morning, everyone. So today we're going to go through two more methods of proving or of mathematical proofs. So the first one is called a proof by exhaustion. So before we actually get into the first question, a proof by exhaustion, as the name implies, just means um, to do a direct proof where we look at every single scenario. So where you look at each case. And of course, we can only do this when it's practical, right? So questions that we've been doing at the beginning of our mathematical proof chapter with induction, when we're looking at an infinite series, obviously wouldn't be practical because we would die of old age before we prove anything, right? Because there's infinite cases. But for questions like these, we would have not just a finite number of cases, but a low enough number of cases where it's actually practical to prove it by looking at each case. So an example that can be completed by exhaustion would be something like this, where it's asking you to prove that if n is an integer such that n squared is even, then that would mean that n is even. And then, of course, we're going to prove it by exhaustion. So a question like this is very practical to do by exhaustion because even though we're looking at every single case, there's only two cases we actually need to look at, so it's not a big deal. So case number one is where n is even. And if we're looking at when n is even, then the way we can represent this is just making sure that n is equal to 2k. I'm just going to use k. You can use any variable you want, but k is an element of integers, right? And now, in order to prove that n squared is even, I just need to square this side as well, so I just end up with 2k, the whole bracket squared, which just gives me 4k squared, and then of course, I can factor out a 2 out of 4k squared, and this shows me that n squared is even. So when I have an even number and I square it, assuming it's an integer of course, then I also get an even number, and now I just need to look at case 2. Case 2, my only other case is where n is odd now instead of even. N is odd. So n is equal to 2k plus 1, right? I need to make sure, so make sure you're very careful when you define things so that they're defined properly. Don't make it k plus 1 because then if k is an odd number and you're adding 1 to it, you actually end up with an even number right off the bat, and then you're just accidentally doing a duplicate of case 1, and then that wouldn't be a proper proof by exhaustion. So I've got 2k plus 1 to define my odd number, and I just do the exact same thing, right? I'm expanding the right side because I need to square both sides, and this will give me 4k squared plus 4k plus 1 when I expand it out. And this proves that n squared in this case would be odd, right? Because I can factor out the 2, but I can't do it for every single term. I can only do it for my first two terms, so then this would tell me that n squared is odd. Okay, so I've proved, sorry, let me just get a little organized here. Okay, so I've proved that when n is odd, n squared will be odd, and vice versa, right? So I'm going to do a double-ended arrow to show that the logic goes both ways. And Same here, when n is even, n squared will be even, and again, the logic goes both ways. Okay. So that's my proof right there. Right. So let's do one more example of proof by exhaustion before we get into our second method. So let me just copy the question over here. So we're going to prove that n cubed minus n is divisible by 3 for all integer values of n. And then I'll write it, oh, sorry, not a very pretty integer symbol, but oh well, by exhaustion. Okay. Now, take a minute, give it a try, and then unpause this video, and then take a look at the solution. Okay? All right. So, hopefully you gave it a try. So now we're going to let n be equal to our expression here, right? So n is going to, big, like capital letter N, is going to be our entire expression. So I've got n cubed minus n. And now what I'm going to do in this case is to factor. So here I'm left with n because they both have n in common, and I'm left with n squared minus 1. And I can take this one step further, and then this is transparently a difference of squares, so I just get n plus 1, n minus 1. And now, at this point, I can build a little bit of confidence, right? Because I can see that these are 3 consecutive numbers, right? This is a number, this is one greater, and this is one less than that number. So it's 3 numbers, one after another. So I know this is going to be true because if I have 3 consecutive numbers, then one of them is definitely going to be divisible by 3, but I have to demonstrate that mathematically. So the way I demonstrate that mathematically is by setting up my multiple cases. In this case, I'll have 3, but making sure that I look at every case. So if we divide n by 3, the remainders will be what? I have scenario number 1, where n is just perfectly divisible by 3, so I have a remainder of 0. I have scenario number, here I'll underline them, scenario number 2, where I get a remainder of 1, and scenario number 3, where I have a remainder of 2. And then, of course, I don't have a fourth scenario because then if my remainder would have been 3, that's not really possible because if I'm dividing by 3 and my remainder would have been 3, then I've made an arithmetical mistake because I can't have that, because then that would just mean that the number would be divisible by 3. Okay, so now I'm just going to run through my scenarios. So scenario number 1, if n is just equal to 3k, obviously super nice and straightforward, then I've just got 3 that I can factor out, so I'm left with k. That's an integer because that's how we defined it. And then that means that big N, so our entire expression, is divisible by 3. Okay, so that's my first scenario. Easiest one. Scenario number 2 is where n is equal to 3k plus 1, right? Because if I divide it and I have a remainder of 1, this is what it's going to look like. Now, what does this mean? If for the first scenario, this was perfectly divisible by 3, and that means that this term right here was divisible by 3, then here, when I'm adding 1, then that means that the factor n minus 1 is equal to 3k, right? Because the minus and plus 1 will cancel each other out. So that means this factor right here is the one that's going to be divisible by 3. So then n is divisible by 3. And extending that logic to our third scenario, we have now where n is equal to, what do I have here 3, oh, I said 3, there we go, 3k plus 2, then that means we get our third scenario, right? Scenario 1, this one was factorable by 3, then this one was, sorry, divisible by 3, and now we've gotten to our third scenario where the factor n plus 1 is equal to 3k, right? Because it would be just equal to 3k plus 2 plus 1, and then of course when I group these together, it would just be 3k plus 3, and then the 3 can be factored out. So then that means this is divisible by 3. And if this is divisible by 3, then that means big N, or our entire expression, is divisible by 3. Okay, hopefully nice and straightforward. And now just at the end, I'm going to write a nice statement. Therefore, by proof by exhaustion, n cubed minus n is divisible by 3. Okay? All right. So that's one of the two proofs we're going to cover today. So that was proof by exhaustion, and now we're going to have proof by counterexamples, but this is the end of this video, so please click on the next video.